Good morning, everybody. I'm Wayne Yip. This morning, 9 o'clock in Taiwan, and welcome to the online seminar. Today's talk will be given by Dr. Casey Honniball. Her title is the study of hydrogen on the lunar surface, which is a very important topic because still, I think from her talk, we will know. I think she will tell everything about the hydrogen atoms on the moon anyway, for one thing. But for me, I'm very particularly interested in knowing the origin of those hydrogen atoms, including H2 molecules. Let me say a few words to introduce the Casey. And she's a native of Nevada, and then she went to Arizona, Tucson, to get her bachelor degree in astronomy, and then she went on to Hawaii. To get her education I suppose, in geology and lunar science. And her advisor is Professor Paul Lucy. And she has, since her graduation, I think she went to Goddard, right? Goddard to serve as a postdoc fellow. And now she stay on there as an assistant research scientist, and working on a number of things, of course, having to do with lunar science, particularly with the hydrogen observations. And she did some very interesting work with SOFIA. I suppose you will talk about that too, the SOFIA infrared telescope on the 747. And because of that, she got the Best Physics Award from the SOFIA project. Okay, Casey. The time's yours now, please.
All right. So thank you for having me today. We're going to talk about water on the surface of the moon and as a view from Earth. So we're going to use two Earth-based telescopes. So the first part of my talk is going to look really at the diurnal variations of lunar hydration using the NASA Infrared Telescope Facility, IRTF, on Mauna Kea in Hawaii. The second part, we're going to focus on molecular water specifically on the moon using the Stratospheric Observatory for Infrared Astronomy, SOFIA. So we're going to first start with some background. Some samples returned by Apollo and Luna have been studied extensively for the past 50 years. And one of the major conclusions from these studies is that the samples are highly depleted in volatile elements. So the plot on top is demonstrating this volatile depletion, including down to hydrogen. However, there were some special samples like apatites, pyroclastic deposits, that showed high water content. The plot on the bottom is from Solidol that shows a profile of a pyroclastic glass bead from core to rim. And we see that the core of the bead shows higher water content than the rim. And that's consistent with water diffusing out of the bead during a volcanic eruption. So these samples, however, are not representative of the bulk moon and actually represent more of a localized anomaly. So the most common rock type on the lunar surface is anorthosite. And it was found that anorthosite only has about 6 ppm of water in the samples, leading to the belief that the moon is mostly anhydrous. So that's why in 2009, when 3 spacecraft detected the signature of hydration on the lunar surface, it came as quite a shock to the lunar community. The observations detected a 3-micron absorption feature across the lunar surface, and this 3-micron band is attributed to hydroxyl or molecular water. So this band is termed total water and is easily seen in the deep impact data where it kind of looks like a check mark in the center plot. Now, this detected was unexpected. However, it could have been predicted. In 1966, Zeller conducted lab experiments where they bombarded silicate glasses with energetic protons and found that the interaction created hydroxyl. They theorized that the solar-wind interaction with the lunar surface would have the same effect, and therefore hydroxyl should be present on the moon, creating a 3-micron absorption band. Later, it was theorized that the formation and abundance of Nanophase iron in lunar grains is caused by solar wind hydrogen producing water. Recently, experiments have shown that recombinant desorption can convert two hydroxyls to water. However, at lunar temperatures, this process is likely inefficient at creating water. But if you add in micrometeorite impacts that introduce high temperatures during the impact, recombinant desorption becomes efficient at converting hydroxyl to water. This idea is further supported by LADEE observations where there are spikes in exospheric water as seen during meteor showers. So the reflectance spectra that were observed by the three different spacecraft revealed a variation in the 3-micron band depth as a function of lunar time of day. Specifically, Deep Impact showed a weak 3-micron band at the equator at local lunar noon, while the morning and evening terminators had a stronger band. It was suggested that the variation in the 3-micron band could be due to molecular water migrating across the surface. However, Tucker and Farrell suggested that this variation instead could be due to hydrogen diffusing through the lunar grains, temporarily binding with oxygen to form hydroxyl. This process would be strongly dependent on temperature. At 3 microns, however, the band depth is not always necessarily due to abundance. So another possibility is that the variation in the hydration and the 3-micron band is actually due to emission infilling this 3-micron absorption band. At 3 microns, the signal is actually a mixture of reflected and emitted light, and this plot on the left shows both of those components overlapping. The removal of thermal emission is therefore really important to interpreting the 3-micron hydration band in spacecraft data. A major issue with the Chandrayaan-1 moon mineralogy mapper data is that it ended right at 3 microns, and this cutoff is right in the center of the 3-micron absorption feature and before the thermal component can really dominate the spectrum at longer wavelengths. This plot in the center demonstrates the effect of thermal emission, with the red spectrum being from high latitude and low temperature, the black spectrum being from low latitude with high temperature. The thermal emission is dominating at the longer wavelengths, but it does have some effect at the lower wavelengths. So the 3-micron cutoff of the M-cube data makes this modeling of the thermal emission difficult and a bit ambiguous. So accurate removal of this thermal emission is greatly improved by observations at longer wavelengths that can strongly constrain thermal models. This last plot demonstrates a thermally corrected spectrum with the longer wavelengths, and you can see that they must make sense spectrally after thermal removal. So there are 3 independent groups that do not agree on whether or not there really is variation in this 3-micron hydration band observed by M-cube. So first, Lee and Millikan report strong diurnal variations at low latitudes and little diurnal variation at high latitudes. Wooler and Grumpe report no variations at low latitude, but strong variations at mid to high latitude. And lastly, Banfield reported no variations at all and instead claims that the 3-micron hydration band is always present across the surface of the moon. Each of these studies used M-cube data and applied a similar but subtly different thermal models. So current spacecraft data are limited and do not fully address this diurnal variation issue. This is mainly due to the limited spectral range and spatial and temporal coverage. One of the most important aspects of characterizing this 3-micron band is the removal of that thermal emission from the reflected component. So in order to do this, we need the wavelengths beyond 3 microns to characterize that thermal component and to remove it. This plot on the left is showing the spectral range of the 3 spacecraft that discovered the 3-micron hydration band, plus the NASA Infrared Telescope Facility, IRTF. All of the observatories except for M-cube cover the entire 3-micron band, plus the longer wavelengths required to constrain the thermal models. This plot on the right is showing an IRTF spectrum with the thermal emission dominating at the wavelengths beyond 3 microns, and the red line indicates the location that M-cube data cuts off. Now, Cassini and Deep Impact observatories had the longer wavelengths, but their observations were limited in spatial resolution and time of day coverage, and therefore they couldn't capture the full story of variations of hydration on the moon. This is where IRTF comes into play and can fill these gaps. So to investigate the diurnal variation, we used the SPECS instrument on the IRTF, which is a high-resolution cross-dispersed spectrograph. The IRTF provides many advantages over the current spacecraft data, such as access to the entire near side at all lunar times of day at high spatial resolution. The image on the bottom here is of Sulpicius Gallus pyroclastic deposit from the IRTF Goddard camera with the slit bore sighted into the center, and you can see some of the small geologic features that we are able to resolve. But the most important advantage of the IRTF was that it provided the longer wavelength coverage out to 4.2 microns. And these wavelengths allowed us to strongly constrain thermal models to address the reality of the observed hydration variations. So the data that we collected for this project included 6 chord profiles that extended from one pole to the other. Each chord was observed on a different night, covering a different lunar time of day. And so the chords that I present today are ranging from 6 a.m. to noon in lunar time and also 5 p.m. or 6 p.m. And additional 5 chords have been collected with the IRTF covering afternoon times and are in the process of being reduced. So here's what we found. This plot shows the abundance of total water or hydroxyl plus molecular water measured from each pole-to-pole chord observed at their different lunar times of day. The size of the point is proportional to the abundance, with hollow circles representing approximately 0 ppm. Now, the easiest trend to see from this plot is that there's a strong variation in total water along each of the chords, where there's an increasing abundance with increasing latitude. Now, diurnal variations are easily seen by looking across the x-axis or across the lunar time of day, but a constant latitude. And what we found is that there's a weak diurnal variation at low latitudes, but strong diurnal variation at mid to high latitudes. There's also an asymmetric trend about the equator, with higher abundances being in the south. This is possibly due to composition because we observed more mare at the northern latitudes. This effect of composition is expected to be small, but especially in comparison to temperature. So these 3 plots show the same results, but in a different view. This first plot shows the 6 different chords as different colors, and the colors actually represent hours from local noon or temperature, with red being the hottest and purple being the coldest. This plot is abundance versus latitude, and the bowl-shaped trend in the chord shows the higher abundances at higher latitude. This middle plot is now the abundance of versus lunar time of day, with the colors now representing latitude, with higher latitude being darker colors. This shows the diurnal variation very nicely, with a sharp drop in abundance between 7 and 8 a.m. lunar time, and then a rise again at 5 p.m. Now, once the afternoon observations have been reduced, we might be able to see and observe the trend after lunar noon to show when the hydration returns to the surface. And this last plot is showing the band depth versus radiative flux. And what we think we're seeing here is that at lower temperatures, there are higher abundances. And so the trend with latitude that we're observing in the first plot is actually not necessarily due to a latitude trend, but to a cooler temperatures at higher latitudes. Okay, so the IRTF provided much needed longer wavelengths to constrain thermal models, making the removal of thermal emission unambiguous. And what we found is that there is diurnal variation in the data, confirming that the variations reported by previous studies are real, and the main contributing factor to the 3 micron variation is likely going to be temperature. Now, the fact that we are seeing a variation in hydration on the moon leads us to question what is causing this variation. Is it molecular water migrating across the surface, or is it hydrogen diffusing through the lunar grains? This question has been under debate for quite some time, but as mentioned way in the beginning, it was theorized that hydroxyl can convert to water via recombinant desorption. However, at the lunar temperatures, this is likely inefficient, but the micrometeorite impacts provide high temperatures, making this process efficient. Now, the species causing the variations has implications. if the 3 micron band variations are caused by hydroxyl, then the variations must be due to hydrogen forming temporary bonds as it diffuses through the lunar soil. If, however, it's water molecule itself that is migrating, then it's a potential source of water to the lunar poles. So recently, there's actually been detections of water ice and permanent shadow using M-cube data and is a definitive observation of the presence of water on the surface of the moon. But for areas that are not in permanently shadowed regions like these ice detections, there have been very little detections of water and only detections that imply the presence of water. So, for example, Lee et al. 2019 detected hematite at the poles on sunlit surfaces, and the maps on top here are showing where the hematite is located. Now, the production of hematite from nanophase iron is promoted by the presence of water, implying that it is present on the moon. Further, observations from the Lyman Alpha mapping project in the UV show that there's an anomalous ratio at local lunar noon where the temperatures are the highest. And Hendricks et al. Explains this ratio by assuming that adsorbed water spectrally behaves like water ice. Now, if this is true, the ratio they see is consistent with less than 1% monolayer of water on the sunlit surface of the moon. However, there are no lab data to support their claim. And it's possible that hydroxyl is responsible for this UV band ratio. Now, reflected spectra at 3 microns can't distinguish between hydroxyl and molecular water, and this is because the band is created by both hydroxyl and water, and hydroxyl can attach to metal cations and mimic the spectral properties of water. Currently, there are no methods capable of separating the two at 3 microns. Water, however, has another fundamental vibration occurring at 6.08 microns that is explicitly due to water without the contamination from hydroxyl. This feature is shown in this plot and is a strong and narrow and well suited for detecting lunar water. This method was new to lunar science, but not new for detecting water in thin section and had been used since 1962. Now, a 6 micron band has even been seen in observations of Apollo samples shown on this left plot, on Mars in the middle plot, as well as in Spitzer data of asteroids as shown by the right plot with the blue spectra. So observations of 6 microns, however, is not possible from the ground as the atmosphere is completely opaque. And currently there are no existing or planned lunar spacecraft capable of making this observation. However, if we get high enough into the stratosphere, the 6 micron region opens up. And so that's why we were using the Stratospheric Observatory for Infrared Astronomy, SOFIA, to conduct the first observations of the moon at 6 microns in search for molecular water. Okay, so here's the data that I'm going to show for today from SOFIA, but I'm also going to try and use the IRTF to understand the differences between 3 and 6 microns, or hydroxyl and water. The map here is outlining the areas that we observed with each, with the blue being the SOFIA Flight 912, purple is SOFIA's Flight 826, and the red is the IRTF. To compare between 3 and 6 microns, I focused on the Viper landing site for the NASA's Viper mission, as close as possible in both of the SOFIA data, as well as on the Mauritius crater, which is circled in black. Now, focusing on these areas of overlap between these two observatories allows us to extrapolate. And so here are the radiance and reflectance maps of SOFIA and the IRTF. Now, you'll notice I tried to align the direction of the IRTF map with SOFIA's maps. Again, the Mauritius crater is outlined here, and these are just to show you the spatial resolutions that we're achieving with these observatories and to provide context for the next slide, which is the maps of water at 6 microns with SOFIA and the map of total water with the IRTF on the right. The scale for these maps is 0 to 400 ppm water. Now, keep in mind that the IRTF map is total water, so hydroxyl plus molecular water. There's a lot to see in these maps, but I'm really going to focus on the Mauritius crater and the Viper site. Looking at the Mauritius crater, one thing that's probably going to stand out to you is that the central peak looks dry in all of these maps. Now, this is a really interesting result for understanding water in the lunar interior, but not the point of this talk today. I'm actually focusing on the floor of Mauritius crater to the right of the central peak. This is where I selected to measure the 3 and 6 micron bands to compare between observatories. The next place to look is the Viper site. Again, it actually only appears in Sophia's map 826, but for this talk, I selected a bottom corner in Sophia's flight 912 to be as close as possible and representative of the Viper site. So now that we've seen these maps and know where we're pulling abundances from, let's take a look at some numbers. The table here provides some statistics for you, but the plot is the easiest to interpret. So I plotted abundance of the floor of Mauritius crater in black and the Viper site in red against lunar time of day. Now let's first take a look at the Mauritius points at 10 a.m. from the IRTF at 3 microns and Sophia at 6 microns. These 2 points are within 1 sigma of each other. This is interesting because it says that the 3 micron total water band is completely composed of molecular water at Mauritius crater at 10 a.m. Now, if we look at other Mauritius point at 12 p.m., what we see is a decrease in molecular water, and thus we would expect the 3 micron band to see a similar trend in decrease. I do have the data for 3 microns at this lunar time of day. However, I just haven't gotten through to processing yet. Now, if we switch over to the Viper points, we again see a decrease in abundance of water with time. And so both Mauritius and Viper are showing variations in molecular water with the lunar time of day. This diurnal variation is exciting because it shows us that water is migrating around the lunar surface on short timescales. Now, when we look further into this with additional Sophia observations, we find that there is a diurnal variation over a range of temperatures as shown in the bottom plot. But based on this additional data, we also found that there is stronger correlation of water with latitude, like shown in the top plot. And this trend is in agreement with M-cube observations and our previous observations of IRTF at 3 microns. So just some things to wrap up and to think about. What we are observing is that most of the 3 micron band appears to be due to molecular water, with the caveat that that was 1 single measurement at 1 location at 1 lunar time of day. The Viper site showed pretty large variations in water with lunar time of day. And there's an instrument on Viper called Nervous that should be able to detect 100 ppm of total water at 3 microns, and so should be able to see the variations occurring, similar to how the IRTF is observing it. Those measurements from Viper will be critical for ground truthing the 3 micron observations, not just only from the IRTF, but also from M-cube and other 3 micron remote measurements. And just a brief note on future work, we really need to do lab work on the 3 and 6 micron bands together to really understand what the water concentration versus hydroxyl concentrations are and to provide better estimates. So there's a lot we still need to learn from these observations, and they're only just the beginning. Thank you. I think that was pretty fast.
It's very fast.
Sorry.
Can you repeat it again? Okay, yeah, that's great. I mean, it's very, I think it's very interesting because Livingston he gave a talk I think last month.
Okay.
And he has a very interesting idea saying that somehow maybe you could tell me more, that he was saying that there would be a subsurface migration of water. And
yeah.
what do you say about that?
Yeah, so some people are thinking that there is water that can migrate down through the surface or up through the surface, depending on the temperature gradient within the first couple layers. And so what we could potentially be seeing is water that is from deeper below that is being warmed up and leaving the surface.
Yeah, I mean, it's really, I mean, you're talking about what just the surface, top surface, few micron or even deeper.
So really, we're talking about a couple grains deep, so not very deep at all.
Okay, that's why it could go by a short time scale. maybe ask the audience first. So anyone has any questions to Casey? Yeah, Lin Qihong, please ask the question. Lin is a high school student. Yeah. All right, please start, Lin Qihong.
Okay, so thanks for your great talk, Professor. So I have one question is because just like you mentioned, so the water emission from the moon, they are highly affected by the solar wind. So my question is because we know that in summertime the moon they will migrate into the magnetic field tail of the Earth. In this time they face for a weaker solar wind strength. And also during the solar storm, so Earth might not hit by the solar storm, but Moon might will hit by the solar storm. So the radiation and the energy level it will rise a lot. So will that change the water emission from the Moon? So this is my question. Thank you.
Yeah, so that's a really interesting question. When the Earth go or when the moon goes into the Earth's magnetotail, we've actually done some observations with the IRTF looking at the 3 micron band to see what happens to the total water band. We're currently kind of confused by it. My colleague Abigail Flom is actually the one leading those observations, and what she's seeing is that it rapidly comes and goes. So once you start entering a lunar eclipse, the water, if you're looking at the subsolar point and you enter the lunar eclipse, the water rapidly appears when there was no water or total hydration. And then once you start leaving the eclipse, then the 3 micron band gets really strong. And we're kind of confused at where this water or hydroxyl would have come from and how it came so quickly. So that's a really interesting question that definitely we are studying, trying to understand what we're observing with the 3 micron IRTF observations. For 6 microns, I'm going to just say we haven't been able to make those measurements with Sophia because Sophia has been grounded and we didn't plan and couldn't plan around observing an eclipse.
Okay, so I have another question is because we know the Earth, they have their own emission tail. So the hydrogen, helium, and also some of the hydroxyl water molecule, there will be emission from the exosphere of the Earth. And it will form a tail in the back of the Earth. So my question is, if the moon they enter this tail, will the surface water or the hydroxyl pollution by the Earth and cause some of the pollution data for the satellite?
Yeah, so it's definitely possible that the moon is experiencing a deposit of Earth water, but we don't know how to distinguish between that type of water and water that's produced from like solar wind or micrometeorite impacts. You'd probably need to go take a sample and look at the isotopic compositions of the sample to know if it's Earth or if it was formed or if it's micrometeorite.
Okay, thank you, Professor.
All right, good. Other questions from other audience? If not, maybe ask another question. How about you mentioned about the LADI mission, LADI observations, and did you see any enhancement during the meteor stream? But just so happened that perhaps you don't have a Soviet observation during meteor stream. Yeah.
Yeah, so LADI was an exospheric measurement of water around the moon, and what they found is when a micrometeorite or a meteor shower was occurring, they found an increase in exospheric water. Unfortunately, nobody that I know of has done any observations to see if like a 3 micron band or has an association with meteor streams. And we have no data of 6 micron with Sophia because we did observing from 2020 until 2022, and we never observed during a meteor stream. I also don't know if we would have been able to see an increase in surface water during that unless we were able to, or how you would distinguish that, unless you were able to distinguish impacts occurring at the same time and that you could observe an impact happening.
Well, at the very end, of your slide, you say that Viper will serve as a ground truth measurement. but we still have some time. Can you tell us something more about the Viper mission and the Viper experiments? Yeah.
Yeah, so Viper is the Volatiles Investigating Polar Exploration rover. It's NASA's first rover mission to the moon in a very, very long time, or I think maybe the only rover NASA has sent. We are going to the Nobile region at high southern latitudes to explore the permanently shadowed and high latitude environment in search for water and water ice. So with Viper, there's going to be 4 instruments. One of them is the nervous spectrometer, which is a near infrared visible volatile system, something. There's the M Solo, which is a mass spectrometer. There's a Trident drill that can drill up to 1 meter deep. And then there's a neutron detector, which can measure hydrogen and below the surface to, I believe it's 5 meters. Don't quote me on that number. So what Viper is going to do is it's going to rove and it's going to explore the southern part of the moon. And it's going to dip its toes into permanently shadowed regions. Using these instruments, it's going to look at how water, hydroxyl, and other volatile species such as methane or carbon dioxide or sulfur dioxide, how those behave on the lunar surface, and really searching for these volatiles, which could be used for future resource utilization under the NASA Artemis program to return the moon.
It's a rover, is it?
Yes.
It's a rover, and then you go down to the you go to the permanent shadow, the region that means at the bottom of a crater.
So there are permanently shadowed regions that are actually not necessarily within the bottom of a crater. So some of these areas are more easily accessible.
So how far you can go, do you think? How far you want to go?
Yeah, so I believe the number for Viper is that we will cover about 90 square kilometers, which is, I guess, the size of Miami in Florida, if you know how big Miami is.
I mean, but what kind of energy are you going to use? Because you're in the permanent shadow region, right?
Yeah, so Viper's not going to be in the permanently shadowed regions all the time. We're mainly going to be roving in sunlight. And so we're using solar panels for our energy. And it's a 100-day surface mission. So during a lunar night, we will park in a safe haven where it's permanently illuminated or mostly illuminated for most of the time. And our batteries can operate for a long enough time that we can explore into a permanently shadowed region and come back out into the sunlight.
Okay, but then how do you provide ground truth for the diurnal variation?
So so that's a really great question. The way I'm going to provide ground truth is actually by looking at the IRTF observations and comparing them to what the nervous instrument is going to see. So the nervous instrument is measuring the 3 micron band, and the IRTF measures the 3 micron band. So what we want to do is take the nervous measurements as it roves across the surface and look at how the time changed with the measurements of the 3 micron band and how it varied with time. So once we do that, we'll be able to say, okay, nervous sees this much total water in the 3 micron band. Now compare that to what IRTF sees at 3 microns at the same lunar time of day. And then we'll be able to say, okay, nervous is the ground truth. And then we have to match the ground truth from nervous with IRTF. Did that make sense?
And because in the permanent shadow zone, that means you're in a very high latitude.
Yeah, so that ground truthing is only going to happen on sunlit surfaces, not within the permanent shadow.
Yeah, in high latitude sunlit region, that you expect to have very large diurnal variation, or if the diurnal variation is a small amplitude, would you able to read to tell?
Yeah, so according to the IRTF and MCube, we think we are seeing large diurnal variations at the high southern latitudes, and so we do expect nervous will see some variations. Whether or not nervous does is to be answered.
Okay, so that's interesting because if those water from of slowing origin, and they have to migrate from the equatorial region or low latitude region to the high latitude region, that means the migration time had to be small also.
That's correct.
Okay, that's very interesting dynamic problem. Okay, great. Any other question for Casey? If not, because she speaks so fast, next time I will ask her to give 2 talks in one hour.
Sorry about that.
Okay, great, Casey. It's still nine almost 9:30, right? In Maryland.
Yeah.
It's time to go to bed.
And it's time for you guys to start your day.
Okay, great. Thank you so much, Casey.
Thank
yes,
you.
hope to see you. Yeah, in person.
Thank you so much.
Yeah, bye-bye.